Module 4, Investigation 2, Comparing Linear and Exponential Behavior. For exercises 1 through 9, as neighborhoods age, local school enrollments can decrease. The local school district has studied trends in enrollment at their schools and has provided the following predictions for enrollment in 2 of their high schools. School number 1, South High School. The current enrollment is 1,980 students, and the enrollment is expected to decrease by 3% per year. School number 2, North High School. The current enrollment is 1,760 students, and the enrollment is expected to decrease by 20 students per year. What quantities are changing in this situation, and what quantities are not changing? So, with the first high school, we can see that the current enrollment is not changing. That's not changing for the second high school either. Like the enrollment that we start out with is not changing, and that's a quantity. Let's see, what else? The number of students that are enrolled in the school each year is a changing quantity. Each year we're going to have fewer number of students at each school. Notice this one is decreasing by 3% each year, and each year we're having a different number of students at the school, so that percentage decrease is a changing quantity. Here the decrease is 20 students per year, so that's a constant decrease. Number 2A, what is the projected enrollment at South High School 1 year after the prediction was made? Okay, South High School. So the first year we have 1,980 students. And then we're going to decrease by 3%. One way to solve this problem is to find 3% of 1980, so we can multiply by the decimal form of 3%, 0.03. That tells us that the number of students decreased by 59.4, which I think that we could round that to 59, because we can't have 1/4 of a student, but we just need to subtract that 3% from the original. And we get 1,921. So there's the projected enrollment 1 year after the prediction was made. Part B, complete the tables below that give the projected enrollment for each high school over the next 10 years. So let's start with South. Was that the one we just worked on? Yep, South High School, which is decreasing by 3% each year. Let's see, here we have the change in time. Well, notice that all these changes in time are just 1 year. Guess we could go ahead and do that for the second table. Let's see, here's years since the prediction was made. Here's the projected enrollment. Remember that in the first year the enrollment was 1,980 students, so we don't have to project that. We already know how many students. We found that this was 1921. To find the next one, I'm just going to multiply 1921 by 3% and then subtract that value from 1921. So I did that just like I did up here. Another way you could do it is to take the current value S, and notice what we really did here was we did 1980 minus 0.03 times 1980. That's the same as 0.97 times 1980, or 97% of our value. So we can just take the previous value and multiply by 0.97. You can check that that would work. If we take 1921 and multiply by 0.97, we get 1863. And I'm going to go ahead and fill out the rest of the table. Okay, I filled out that column. Now we need delta S. Remember that this change, delta S, is the final value minus the initial value. So that's 1921 minus 1980. Negative 59. To find the next one, we do 1863 minus 1921. That's negative 58. I'm going to go ahead and fill in the rest of this table. So you might notice I rounded all of these. You might have slightly different answers. I mean, it's not going to be exact when we're talking about enrollment, since we're having to round off. But you should have some similar values to these. Okay, now let's talk about North High School. So the initial enrollment at North High School was 1,760 students. And then we're just decreasing by 20 each year. This is a lot simpler than the last one. We just gotta subtract 20 each time. Okay, got that. Now the change is just the final value minus the initial value. Notice we just decreased by 20 each time. Each one of these is going to be negative 20. Okay, great. You should have tables that look kind of like this. The numbers should be really close, if not exact. Part C says, describe how the projected enrollment at South High School changes each year. So here we see that we're our projected enrollment is decreasing, and here we have each of the changes. Negative 59, negative 58, negative 56, negative 54. This is actually an increasing change. My first instinct was to say that it was decreasing, but note that we're at negative 59, and negative 49 is greater than negative 59, so we're actually increasing as the number of years increases. Notice that the change in S with the change in time is not constant. It's actually exponential. Part D says, describe how the projected enrollment at North High School changes every year. That one was decreasing too, but remember that it was decreasing by a constant amount. We're decreasing by negative 20 each year. That change in enrollment is constant. Notice that if we took the change in the enrollment divided by the change in time, we'd always get negative 20. We have a constant rate of change. This is a linear function. Question 3a, what decay factor or number is each year's projected enrollment multiplied by to determine the next year's projected enrollment for South High School? That's the 0.97. Remember when I showed you guys this here, we can just take each of these current enrollments, multiply by 0.97, 97% to get to the next enrollment. We call this a decay factor because we're decreasing each time we multiply by the factor. Part B, explain how you could determine the decay factor from Part A given only the table you created in 2B. Okay, this is going to be really cool. Let's see, if you take and just pick two consecutive values like 1921 and 1980, and let's divide 1921 by 1980. Do that in your calculator. What do you get? should get 97%. If you take any of these values and divide them, you'll always get the same ratio. Because remember, we just multiplied by 0.97 each time to get the next number. So we can find that growth factor by just taking the ratio of consecutive values. Number 4. Define two functions that express the projected enrollment of North High School and South High School as functions of the number of years since the projections were made. North High School, n equals f of t, where f of t equals, well, which one was north? North was the one with the constant rate. That's a linear function. Notice that we just take and, let's see, we take our original value, 1,760, and then we're decreasing by 20 each year. So we take negative 20 times the number of years, t. You could have also written this in the familiar slope-intercept form, negative 20t plus 1760. So there we have our linear function. South High School, that was the exponential growth. The original value was 1,980. And then to get to the next year, we multiply by 0.97. Now if we wanted to go 2 years ahead of time, we'd multiply 0.97 times, or squared, we'd multiply by another factor. So this is our exponential function. You could have also written something like 19, no, I can't think of anything else you could have written there. Sorry. You should confirm that those tables work, I'm sorry, that these equations work to generate the tables. Just plug t equals 1, t equals 2, t equals 3. If you don't already understand these formulas, just take a second and look at the table and see how they work. Number 5, create a graph of the projected enrollment for both North High School and South High School in terms of the number of years, t, since the projections were made. Be sure to label the axes. Then determine the practical domain and practical range for each function. Okay, so all we got to do, let's see, is this is going to be our t-axis here, time, and the y-axis will be the projected enrollment. And we just need to look at our graphs here. We have up to 10 years for each of these. So this will be year 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, it looks like we have enough room. We might could go to, let's see, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yeah, let's do each one of each. So this will be a year here. We'll have 2 to make a year. So we can get a fuller graph. We'll be able to examine it easier. And then we need a good scale for this y-axis, or vertical axis, I really should say. Notice our projected enrollment, like the highest value we get is close to 2,000. The lowest one is around 1,400. We need to fit that range in the graph, 1,400 to 2,000. So let's make as high as we can go 2,000. What does that make these? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2,000 divided by 10. So that's 200. Notice that I've already went ahead and labeled these 200, 400, 600 all the way up to 2000. So now we just need to fill in our graphs. I'll use the blue for South High School. So 0, 1980. So over here on my graph, for year 0, I'm just going to put a blue dot at 1980, which is maybe somewhere like right here. Now after 1 year, it is 1,921, and remember we used 2 of these spaces for 1 year, so 1921, somewhere about right there, and I'm going to go ahead and fill out. It doesn't have to be perfect, but that's what we got here. And now for the second graph, I'll do that one in green. Honestly, these changes are so small, it was really hard to make this graph. We're only decreasing by 20 here, and this is a scale of 200. But you should see this pattern. The green starts lower, but then it ends up higher than the blue curve. Okay, what's our practical domain? The set of possible input values. You might want to say something like all real numbers or something, but we're only looking at the enrollments each year. Really, we have, notice that we have these dots here. We don't have a continuous function, we have a discrete function. Really, the set of all possible inputs are just the integers, the positive integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can have 0, 2. So we can say that as the positive integers. Okay, to be consistent, North High School is blue, South High School is green. And the practical range, the set of all possible outputs, notice that for North High School, the highest we could go was 1980. And then we're decreasing, so it's possible that this function could go all the way down to 0, I suppose. That's population. And then something similar for South High School. We could decrease all the way down to 0, or any number in between, any integer in between, let's see, 1760 and 0. We should note that these are only integers, not all real numbers, because we can't have a fraction of a kid. 6. Determine and interpret the meaning of the vertical intercept for the projected enrollment at North High School. Okay, North High School, the blue, the intercept is right here. That's the vertical intercept. We usually say the y-intercept, and that, remember, was 1980. So we could write that as an ordered pair. The time is 0 and the output is 1980. That means that the initial enrollment of North High School was 1980. Okay, and for number 7, determine and interpret the meaning of the vertical intercept for the projected enrollment at South High School. Well, that's 01760, and that's the initial enrollment of South High School. And I probably should have specified the units in number 6. Number of students are the units of the enrollment. Number 8, using your graph and/or table of values, determine when, that is, after how many years, the projected enrollment at South High School will be less than the projected enrollment at North High School. So we see that the change is coming right about here. They switch. On my graph, that looks about year 6. My graph might not be perfect. Let's go to the table of values. So here we see that 1980, 1760, South High School is always in the lead all the way down till at year 6 it's still in the lead, and then year 7 is actually when South High School is smaller than North High School. Number 9, find and interpret the following using n equals f of t and s equals g of t as defined earlier. F of 6. That was our function for enrollment at North High School. So f of 6, let's see, we can just plug 6 into this function. Negative 20 times 6 plus 760. I got 1640, and that tells us that after 6 years the expected enrollment will be 1,640. Okay, g of 3. Remember that function g of t was 1980 times 0.97 t. So we just substitute a 3 in place of the t and we get 1807. That tells us that after 3 years the population, or the projected population of students at South High School is 1,807. G of 6 minus G of 2, we can calculate this difference, and we should get negative 214. So this is a difference in projected enrollments, but if we think more about what this tells us, it tells us that as the time increases from 2 to 6 years, there's going to be a decrease in projected enrollment. Okay, G inverse of 1600. That's just going to tell us what year, how many years, such that the population, the predicted population is 1600. So we'll have that 1600 equals 1980 times 0.97 t. And we need to find out what t is. One way we can do it is just to go look at our graph and sort of estimate. Actually, it tells us t is 8. So there you go. That was actually the table, not the graph. You could also solve that equation using a logarithm. Okay, let's see if we can tackle number 10. A neighborhood is being developed and they are opening a new high school, Bayside High School. Experts predict that enrollment at the school will begin at 940 students and will increase by 4.3% each year for the next 10 years. Okay, so here I want to just notice something. We're increasing and by 4.3% each year. So what will the expected enrollment be next year? I start with 940. I'm going to increase by 4.3%, so I'm going to add 4.3%, which is 940 times 0.043. Another thing I could do, it's really this, just another method. I could multiply by 100 and 4.3%, which is the same as multiplying by 1.043. If you don't believe me, check and make sure those are the same calculations, and you might want to think about why that's true. So we get 980.42, or about 980 students. Okay, then after 2 years, this is how much it was after 1 year. So then after another year, we just multiply by that same growth factor, 1.043, or 940 times 1.043 squared. This is about 1023. How can we compute the expected enrollment in a certain year if we know the enrollment from the previous year? Well, we could always just multiply by 1.043, or you could take the previous year and you could add the previous year, multiply by the 0.043, whichever way makes sense to you. Part D, I. Express the expected enrollment at Bayside High School as a function of the number of years since the projections were made. So our function, I'm just going to call it f. We take 940 and then we multiply by 1.043 times the number of years. The next question says, what is the 1-year growth factor for this situation? So if you go look at this next table, let's see, the structure of an exponential function is of the form f of x equals a times bx, where a represents the initial value and b represents the growth factor. So there's that b raised to the x. So in our problem, the growth factor is 1.043. So note that what this tells us is the expected enrollment for any given year is 104.3% of the enrollment the previous year. Part 3, for equal changes in the amount of time since the prediction was made, is the change in the enrollment constant, or does the amount of change in the enrollment change? Okay, this problem is a little bit tough to make sense of. So let's say that we had a change in time of 1. If we look at the change in enrollment from some, let's see, final value, and then we subtract the change in enrollment from some initial value, which is just t minus 1 year earlier. What do we notice? Well, because I do lots of math all day, I notice that I can factor a 940 times 1.043 t minus 1, and that gives me 1.043 minus 1. Which is just 0.043. But notice that this change in enrollment that I just found is actually a function of t. It depends on which year I'm at. That change is not going to be constant. It's going to change as the enrollment changes. You could think that each year the percentage increase is going to get larger and larger since the population gets larger and larger. Okay, here's a lot of stuff. I'm not going to read that to you at the moment. but it's really important and you should read it if you haven't. And think about it. 11. For the following situations, determine the 1-year growth factor and 1-year percent change. Suppose you know the projected enrollment for Mountain View High School in 3 years is 1,829 students, and in 4 years is 1,893 students. And you know the projected enrollment is increasing every year by some factor. Call this factor x. How do you find x? This number is called the growth factor. No problem. Notice that we have 2 consecutive years, from 3 years to 4 years. So to find the growth factor, all we have to do is divide final year minus the initial year. This only works if they're consecutive, because if there is a growth factor, we would just multiply this number by the growth factor to get this one. So it makes sense that we can just divide. 1.035. They didn't really ask us for the 1-year percent change. They sort of did, but it's 3.5%. Part B. Suppose you know the projected enrollment for Vista Groves High School is growing by some constant factor every year. Determine this factor given that the projected enrollment for Vista Groves High School in 5 years is 1,565 students and in 6 years is 1,643 students. Okay, same thing. Just divide those. 1.05, and that means that our percentage increase is 5%, percent change is 5%, and there's the growth factor, 1.05. Again, if this isn't quite clicking, note that 1565 times 1.05 is 1643. And so I know that if I was kind of working backwards, if I divide here, I can get the 1.05. Part C, give an exponential function that grows by some constant percentage every year, and 2 output values for year n and year n plus 1, where n is some positive integer. Describe how to determine the growth factor for this exponential function and explain why your method works. Well, basically, I just have to divide the value for the nth plus 1 year divided by the value for the nth year. The reason being is if you know in, say, year n, you have some value, and then in year n plus 1, your value will just be the value of the previous year multiplied by the growth factor. I really like to look at it mathematically. Let's say that a is the initial value. Then for year n, we'll have a times our growth factor. Let's call that k to the n. And then for this year, we'll have a times k to the n plus 1. If we divide those, we'll just get k. That's because k to the n plus 1 can be written as k to the n times k. So we have a times k to the n here in the denominator. These cancel out and we just get a k. There's our growth rate. So I'll say it again in words this time. To find the growth rate, we simply divide the output values for consecutive years. It's that final divided by the initial. Growth factor. Okay, that was a lot of information. Good luck with your future homework assignments.